Today we are explaining the paper data pyramid for embodied manipulation. It asks a practical question. What kinds of data can teach a robot not only to recognize a scene, but also to choose and execute a physical action?
Why is ordinary internet scale vision and language data not enough for that job?
A language model can learn from images and text without knowing the physical consequences of an action. An embodied model needs observations tied to states, motion, contact. The paper therefore treats embodied data as a family of sources with different strengths.
What structure does the paper use to compare all those sources?
It organizes 5 layers in a pyramid. Real robot data sit at the physically grounded end. UMI style data use portable human-operated interfaces. Egocentric and exocentric recordings capture human activity. Simulation produces scalable synthetic trajectories. General vision language data provide the broadest semantic coverage. Moving down the pyramid generally increases accessibility and scale, while moving up brings data closer to executable robot control.
So the pyramid is not ranking one layer as universally best. It is showing which kind of supervision we gain, and what we give up when we move between layers.
Exactly. The paper compares each source by quality, diversity, reassignability, and physical fidelity, then asks how a model can combine them for perception, reasoning, planning, action generation, and world prediction. That makes the gap in earlier work concrete. Individual datasets solve individual bottlenecks, but their collection costs, action formats, and physical meaning do not line up automatically. The paper's approach is a data-centric survey. It reviews how each layer is collected, what signals it contains, how those signals are converted into supervision, and how recent embodied foundation models mix the sources during pre-training. This is the method diagram for the argument. First define the layers, then connect their properties to model capabilities and open problems.
The timeline seems to show a shift from one dominance or stored mixtures. What does each mixture contribute?
Real robot trajectories provide the closest link between a command and its physical consequence, including sensor noise, latency, contact dynamics, and hardware limits. UMI data make collection more portable and robot-free, while preserving relative and effector motion. Human videos add long horizon activity and hand-object interactions. Simulation supplies varied scenes, object states, general data fill-in language, visual concepts, and broad semantic knowledge.
The UMI side is portable, but the robot still has to execute the recorded motion. Where does that conversion become difficult?
UMI records relative and effector trajectories from a human-operated interface. Retargeting must map that motion across embodiments, sensors, coordinate frames, and grippers. Real robot collection avoids some of that conversion, but it is slower and tied to the platform. This is why the two sides are complementary, rather than interchangeable. The paper also separates data by the capability it supervises. Segmentation and localization tell a robot which object or functional part matters and where it is. Planning date, a turn a goal into ordered subgoals. Physical reasoning data predict collision, stability, object permanence, or future state. Failure data identify where execution broke down and what recovery action may help.
That explains why a successful demonstration is not the whole story. A policy also needs examples of uncertainty, failure, and the next safe correction.
Right. The survey highlights human-in-the-loop collection for exactly this reason. Instead of recording another complete success, a supervisor can intervene at a difficult state in data correction or recovery trajectory. It also warns that useful auxiliary signals, such as contact maps or human hand poses, do not directly specify an executable robot gripper pose. A separate class generator, retargeting method, or optimization step is still required.
What evidence does the survey give that data composition is changing in actual models, rather than only in the taxonomy?
Its model timeline shows recent systems increasingly co-training real robot, egocentric, simulation, general, and UMI-style data. The model families also expand from action-centric vision language action systems toward world model augmented and unified world action systems. The result is a design trend, not a single benchmark score. Broader mixtures are being used to support perception, reasoning, planning, control, and prediction together. The survey identifies a second alignment problem inside the model. Actions from different robots do not share one obvious coordinate system. Some methods keep embodiment-specific action heads. Others use a fixed dimensional vector with masks. For the motion itself, actions may be robot-centric, camera-centric, or wrist-centric. Each choice changes how easily behavior can transfer, and the paper notes that controlled comparisons are still limited.
So what are the main limitations on next steps that follow from this comparison?
The paper points to 6 priorities. Robots need large-scale tactile data for contact-rich skills. Datasets need more failures and recoveries, not only clean successes. Collection pipelines must become scalable across the pyramid. Actions must align across embodiments. Egocentric data should be turned into useful pliers for dexterous hands. And training recipes need principal tools for deciding which sources to mix, in what amounts, and with what quality conditions.
Then the central lesson is not that robots need one giant dataset. They need a deliberate combination whose scale, diversity, physical fidelity, and action alignment match the capability being learned.
That is the paper's conclusion. The data pyramid turns a scattered collection of robot, human, simulated, and general datasets into a set of complementary tools. Its evidence supports mixing sources, while its open questions show that better transfer will require better physical signals, better failure coverage, and better alignment between what a dataset records and what a robot can actually do.
A useful map for designing the next generation of embodied learning systems.